5.5. People from my previous class probably a little bit surprised. We're changing the book. So now it's back to 5.5. And they call it substitution rule. Or we're going to call it U-sub. Because in America we use U all the time. So it just makes sense to call it U-sub all the time. But that's not the rule. You don't have to call U all the time. And I will jump into the example right away to show you what's the point of the problem. It's just smart to show you the problem and then like ask you, interesting, what's going on? A cosine of x to the 4 plus 2 times 4x cubed dx. Do you still remember any of this notation, integrals and stuff? That's what my lecture 0 was about, to review those things. Now, how would you integrate that? And our job is to teach you how to integrate those things. The U-substitution basically unfolds chain rule. Do you guys remember chain rule? Yeah. Do you remember what chain rule is? And I'll show you in a second why chain rule is involved here. Our idea would be to simplify this weird long integral with product over here and parentheses inside of the cosine and so on into something we know how to integrate. We know how to integrate cosine, so the integral of cosine is sine, then maybe whatever you see is complicated inside of the cosine can be renamed. When you say R letter, that's the Russian thing. So called U, and that's why we call it U-substitution. And the notation is, we say, let U be x to the 4 plus 2d, plus 2. Then, when you renamed this integral, no, the cosine of the inside part, it becomes cosine of U, right? So that's already looks better. That's the idea. It already looks better. But what happens to the right side over here? We cannot like abandon it. It's supposed to be converted into U. And that's where the derivative comes in. You see this dx over here, this dx? This dx means the moment you introduced new variable, now you have to find a derivative of that new variable. So let U be x to the 4 plus 2, then du is, you need to find a derivative of that right away. Derivative of x to the 4 plus 2 is 4x cubed. But remember we had differentials topic like years ago. You put dx at the end. And that idea I can review really briefly. Du over dx, that's the notation of the derivative, is 4x cubed. So what we do, we're just basically multiplying by dx to have a better notation. 4x cubed dx. That was the topic called differentials. Differentials. Topic from Calculus 1 class. You can review it if you want. Not very important, honestly, just that makes sense. Look at this. I multiplied by dx if you imagine this is a fraction, and it jumped to the right-hand side. So I'm putting this in the brackets like this. That's the habit I have, because these brackets will be important. If you do your substitution 5 times in a row, you can see your brackets everywhere in your notes, and you see what changes did you do. Why this change was convenient? Because when I differentiated to U, I got 4x cubed dx. And it's exactly what I'm having here. 4x cubed dx. Magic. Well, it's not magic. That's how the example was created. I created this example the way that this is going to be a perfect match. So cosine of U times, you see this? I'll use orange color here. Red, purple. If inside piece is U, then all this piece matched with du. And then the integral becomes cosine of U du. That's the idea. Now we're integrating a function called cosine, just with respect to different variable. It used to be something with x, now it's something with u. So what? We still know the answer. The integral of cosine is sine or minus sine, which one? To check, you differentiate. Derivative of sine is plus cosine. So the answer is just sine of u. You see, not x. We're differentiating cosine in terms of u. Don't forget plus c if it's indefinite integral. And this is the answer in terms of u. Since you're the only one here, well, that's like 90 people in class, but still, You're the only one here who did the substitution. You're the scientist. You're doing this for the scientific purposes in your lab. Your lab mates don't do it with you. You use this U as intermediate helper. This U made your cosine easier, and then even helps you to rewrite the integral in terms of easier variables. But nobody knows what U is, so your job is to go back to the original variable. In this case, it was X, because your coworkers will have a meeting with you and they will say, okay, so what's the output if we're using 5 million injections for this hospital? The injection will be in X terms. So you cannot say, I have answer in terms of U. Nobody knows what it is except you. So you're reminding yourself, U is actually X to the 4 plus 2. And that's why I made this funny example in the lecture 0 about love with the heart in it. Because you take this X to the 4 plus 2 and brutally plug it into your sign, preserving everything. X to the 4 plus 2 plus C. And that's the answer. So just like I mentioned in lecture 0, check my fun example with love. If I tell you to plug U, which is X to the 4 plus 2, everywhere you see U, you just copy and paste it there. So idea. We're having the integral, it looks complicated, and we're gonna have lots of complicated integral in the next months, 2 months, I would say, 1.5 months. This integral has cosine with something in it. And that's how you're like, so you should just think, if cosine has something in it, maybe let's make it easier. And let's choose whatever is inside to be some just letter, and just people like U-substitution, so they call it U. By making this substitution, you made the whole integral easier, and the integral of cosine of X to the 4 plus 2 times 4x cubed dx is sine of X to the 4 plus 2 plus C. Check yourself. The cool part of this idea for your homework and exams is that you can check your answer. You can, how to check the result of integration, do you know? Who knows?
Derivative.
You just define a derivative, exactly. Let's just differentiate the answer. Sine X to the 4 plus 2 plus C, and I'll put huge prime on top of all of this. And then, to everyone. Okay, now you can chat to everyone, I just noticed. So when I'm differentiating it, chain rule happens, and that's where you have to remember chain rule. Chain rule says, just like in the Russian doll, you first differentiate the outside doll. You know, if I always like this example, of course, why not? Like the outside part of the Russian doll. The outside part is sine. Derivative of sine is cosine. Preserve everything you see inside. That's what chain rule says. Do not touch it because you did not open it yet. When you finish differentiating sine, now you can look at the Russian doll piece inside. Inside, you have X to the 4 plus 2. That's the step inside. That's what chain rule does. Chain rule says, chain by chain, you dive deeper. Derivative of X to the 4 plus 2 is 4x cubed. Then what happens plus C? Plus C gives you 0. So let's compare this piece exactly what we had inside of the integral. Cosine of X to the 4 plus 2 times 4x cubed. So the answer is correct. And that's a good part of it. Literally during the exam, you can check yourself. Go ahead. Okay. Do you have to be so annoying? Nope. Okay, good. So U-substitution undoes chain rule. That's the idea. Note. U-substitution was created. U-substitution undoes the chain rule. You're supposed to put the in front of it. And that's chain rule. That's an interesting thing. So we were fighting with chain rule in calculus 1 so much. Remember the mastery exam when we like tortured you here and there. And then after all, when we learned it, when we learn integration, it makes sense that now we need to figure out how to undo chain rule, because integration undoes differentiation and vice versa. So U-substitution, as the first topic we learned, was created to undo what chain rule does. In the original formula, there's a formula. So we call it the substitution rule. the substitution rule. It doesn't have to be U-substitution. Again, U is just convenient notation, but actually it can be your first letter of name, J, M, whatever you want. This is how it looks like. If you have U, that's the substitution we do, which is your function g of x. That's the inner function. This function should be differentiable. Let's do A. Differentiable function with or whose range on interval I, so it has a domain and range. Range is an interval I. And there's one more function, f, and this function is continuous, C-O-N-T, continuous, on that interval I. So continuous means no breaks, no jumps, no gaps, no holes. Then, now use green color, then integral, let me do fat one. Integral of f, so f is my outside function in the Russian doll, if you think about it. G of x, that's going to be my U substitution. That's exactly what this notation means. U is g of x, so g of x is going to be whatever I call U as a U substitution. Times g prime of x at the tail dx. That is the piece which we called du. I'll point out in a second. Equals integral, and the integral becomes simple f of u du. So from complicated integral into the simple one. Now this is the idea of chain rule. Here it is. And then I'll show you in orange what we're talking about here. This is my u, g of x is u. Then when you differentiate g of x, you will have g prime of x dx, that's my du. That makes sense that integral becomes f of u du. So you're renaming some parts of the integral to make it more simple, to undo the chain rule. That's the idea, undo the chain rule. This formula looks messy. You don't have to remember it, honestly. You need to know how to apply it. So that's what we're gonna do right now. We're gonna do tons of examples, and that's where I'm gonna be asking you, did you get it or not? But this is the official definition of it. It's basically renaming something and rewriting the complicated integral into simple form. Okay, examples. Some of these examples are from your homework, so definitely pay attention and then make good notes. I always say make good notes. So, example 1, let's integrate a square root of 2x plus 1 dx. And I'll show you two ways of doing it. Two ways of doing it. And then you will choose the way you like and probably will stick to it for a while. So way 1. It's just two different ways to see the problem, that's I would say. And I was trained to do one way, and then other students are trained to do the other way, and it's fine. They're both correct and they're both good. So just figure out which one you like more. Okay, this is how you look at it. I see integral, and you should have this kind of feeling, I don't like something about this integral. And I'm looking at it, and I don't like the square root. Like, who likes working with squares? Just like we had cosine of some stuff inside. If you don't like something inside, call that u. Not the whole thing. I mean, if you don't like the whole integral, that's kind of a bad thing. But I mean, something inside makes the integral complicated. I know what's the integral of a square root. That's just power rule. We're going to do that. You will see it's not too bad. But I don't know what's the integral of a square root with some stuff in it. So it makes sense to call that stuff u. See? Because have a good imagination. If I'm going to call this stuff u, the integral will be square root of u. And that was the first thing we taught you when we learned antiderivatives. Square root of u, that's power rule. You can do it. It's 1/2 plus 1 over 1/2 plus 1. So way 1 is, and here's notation I learned in Ukraine. I do huge square equal sign like this, and you don't have to follow this notation. I always point this out. And I write down on the top of the equal sign, my u is 2x plus 1. And then I immediately need to find du, because that's what the formula says. Look at the formula, it's in front of you. You did not find you, the one who chose you. You chose your u the moment you did, find du. What is derivative of 2x plus 1? 2, but don't forget dx at the end. That's important. And I even put it in the brackets because brackets are easily to find when you look into your notes. So you see this notation, the equal sign with the brackets on top of it. When I came to the United States, I was using this notation, and then one local professor did not like it. So he took points off for me doing this. It's interesting. So I'm not going to take points any way you like it. You can put it in somewhere in the corner. You can use pencil. You can use pen. But just don't do it instead of the equal sign. It's supposed to be somewhere, but equal sign should stay, because equal sign means equals. Okay, okay, I'll do like this. My u is 2x plus 1, then it makes sense then that the integral becomes a square root of u. That's the easy part. I hope you got it. 2x plus 1 is u, so now it's square root of u. But what happens with the x? The x is like a literal thing. You cannot just drop it like this. And that's why two ways show up. Two ways how to figure out the dx part. Way one is to actually think about it. And the thinking about it means it would be nice, like in the previous problem, I had perfect match. Du gave me 4x cubed dx. And I had exactly 4x cubed dx. And that's exactly how I just rewrote it. 4x cubed dx was renamed to be du. In this example, du is 2 dx. But instead of just having dx, that would be nice to match it. So let's do it. Let's just match it. I'll put this 2 in front, and then I'll say, yeah, matches. 2 dx. I need 2 dx. I made it. So like, why not? But you cannot just multiply everything by 2 without consequences. So the first way is, that's the first way I like doing it. I'm multiplying by 2, then outside of the integral, I will divide by 2 to make sure that they compensate each other. If I multiply by 2, then I have to divide by 2. But this 2 inside of the integral will help me to rename this little piece over here to be du, because it's exactly du. If inside piece of the square root is u, then the tail, I call the tail 2 dx, it's perfect du. Then I have rights to write down du and finish the integration. Way one is to fix the integral. Fix the integral to make sure that it's working. That's the idea. So now we're gonna finish the integral, and I will show you the second way, because I can see not all students like doing it, because this requires a little bit of imagination. In this case, I need to multiply by 2, and so I divided by 2, but sometimes it's more than that. What is the integral of square root of u du? If you don't remember, take a pencil and write down square root of u as u to the 1/2. Then it's basically power rule. Power rule tells you, I reviewed it in lecture 0, watched if you didn't. It says the answer will be u 1/2 plus 1 over 1/2 plus 1. And don't forget plus capital C. With your homework, if you forget capital C, it will not like it. So don't forget. Okay, that means it's basically u 3/2 times 2/3. How do you know why 2/3? Because I'm dividing by 3/2 plus c. There's one mistake in these calculations. Did anyone pointed this out? Some mistake which will be important. So I want you to remember it. The integral is square root of u du, and there's this extra 1/2 in front of it. It showed up when I changed everything to u. So I have to keep carry it everywhere. 1/2 in front of the integral, 1/2 in front of the calculations, 1/2 in front of the answer. And you can just basically multiply it. 1/2 times 2/3 seems to be 1/3. So the answer is 1/3 u to the 3/2 plus c. So I will wait for a second and check. Chat. No, it should be good. Okay, that's good. Chat if you have questions, or definitely be brave to unmute yourself and ask. That's not the end though. So I will be asking this, is this the end or not? Nobody knows what U is. You're the one who created it, except you don't have notes about it. So if you present this answer to people, they will not get it. They will like, wait, we started with X. Why your answer has U or J or M? What did you do? And you have to go back to your notes and say, oh, I did U-substitution. They will tell you, we don't care what you did. Give us the answer in terms we can understand without asking you for help. There's like 35 people in the lab. Why we have to email you for this detail? So since nobody knows what U is, you have to give the answer in terms of original function. And I will remind myself that U is 2x plus 1. You don't have to do this reminder all the time, but I'm like doing it. Then the answer will be 1/3 U raised to the 3/2, but U is 2x plus 1. 2x plus 1 raised to the 3/2 plus c. And put it in the box. That's the answer in terms of the original variable, parameter, whatever computer scientists know. You can have lots of variable, dummy variables. That's the one, the answer with the original variable. And you can check yourself by differentiating this. It's supposed to match with the square root 2x plus 1 if you're differentiating this. So that's way 1, matching the tail with du. Way 2 is more straightforward. So many of you will like it more. But I always stick to way 1 because I like the creativity of it. That I needed to have 2dx, and I made it happen, and I kind of feel satisfaction out of it. Way 2, I'm looking at the original integral. I will even write it down. Integral a square root of 2x plus 1 dx. This is what I was given. You ask yourself, okay, U-substitution, what should I do? You like scratch your head, and then you realize, I don't like the square root. So let me choose the function inside to be U. And then in your imagination, you imagine if I would have integral of square root of U, you know how to integrate, so it's good. Then I will have exactly the same notation as I did before, but I will do it below. That's what Americans do, I will tell you. Like I can see not all professors liking me putting it above the equal sign. I will do it separately, maybe even with pencil or different color. I will do U equals 2x plus 1. Then du is derivative of 2x plus 1, that's 2, but don't forget dx. And I put it in the brackets to visualize it. Now, I do have u there, but I need to find dx. In the way 1, I made dx to match with du by multiplying by 2. But if you don't like doing that, you literally solve for dx, the second part of these brackets. Solve for dx. So dx is du over 2, or I will do 1/2 du, right? 1/2 du. I'm literally solving it. Oops. Solving for dx. And that means you don't have to be creative anymore. Like it literally tells you what to do. Dx, if you're substituting if you're substituting 2x plus 1 with u, then you're substituting dx with corresponding 1/2 du. And it's exactly what we had. I will show you in a second why it's exactly what we had. Because now we're going to have integral, a square root of u, 1/2 du. That's what you got from solving for dx. But you can always kick out constants out of the integral. So I will have 1/2 integral, the square root of u du. And it's exactly the same thing we had in case 1. In case 1, I made it to be 1/2 in front of the integral. Here it is. This 1/2 showed up because I multiplied by 2 and then I divided by 2. That's why it showed up. So I was creative enough to make it myself. But in this case, I did not have to be creative. I literally solved for dx, and then I did like this. I plugged it in. So here's my u, I'm plugging it in, and here's my dx, I'm plugging it in. And when I plugged in, the integral just showed up by itself. And that's the idea. And then the answer is the same. The result is exactly the same. The integration is exactly the same because the whole situation is the same. So the answer will be, I will do 3 dots, 1/3, 2x plus 1 raised to 3/2 plus c. We're going to check the result in a second. Okay, ask me. What do you think? Chat. Here it is, finally found it. So let me do this. So do you all see what I'm writing or not? I think now I shared. Yeah, okay, good. Yeah, let me know. And definitely unmute if you don't hear me or you don't see me. You should unmute and tell me, or chat. I check chat all the time. And that's the idea of U-Substitution. Choose the way you like it. And do the quick check if you have time after the exam. I would do the first exam especially. You can do that quite a lot. Check. To check the answer, I will differentiate 1/3, 2x plus 1, the raised to the 3/2 plus c. I will put huge parentheses and I will differentiate it. This is a chain rule. Well, duh, because we use U-Substitution for chain rule, so that makes sense. Chain rule says, look at the function outside. I see some kind of function, and now you see, now you know why I called it u in calculus 1 class. I kind of mentioned to you, imagine it's a function u, which is raised to 3/2 and multiplied by 1/3. I mentioned in calculus 1 class because I knew that we're going to be doing U-Substitution in calculus 2 class. So I told you before, soon we're going to be calling it u all the time. So it's a function raised to the 3/2 power. I know how to differentiate that. 3/2 goes down, copy 2x plus 1, copy, that's what chain rule says. Decrease 3/2 by 1. 3/2 minus 2/2 becomes 1/2 times, chain rule says don't stop, that's where the chain rule steps in. Now chain rule says looks inside. Look inside. Inside I see 2x plus 1. Derivative of 2x plus 1 is 2. Derivative plus c is 0. That's simplifying. 2 cancels out with 1/2. 3 cancels out with 1/3, and the answer becomes 2x plus 1 to the 1/2. But what is that? That's a square root of 2x plus 1. That's exactly what we had inside of the integral. So the answer is correct. You can put like a huge fat rainbow check mark. Yeah, check. So that's how you know. You check yourself. That's like a beauty of it. More examples. With more examples, you will get a better intuition what to choose your U with. And I know your posts in the campus wire in the forum will be, what should I choose for you here? And that's a pretty cool part of it because it's a game. In mathematics in this class at the beginning is basically a game where you have to decide what to choose to be U. So here it is, integral of e raised to the 5x dx. What your intuition tells you, what you don't like in that thing. And you cannot say you don't like all of it. It's very rare actually when everything should be u. Usually some piece should be u. And then you should tell yourself, what do I know how to integrate? We know how to integrate exponential functions. I reviewed that in my first 0 lecture. But this one has 5x in the exponent. And that's what I don't like. It makes it more complicated. So that's like, you know, you have a feeling about it. That's where intuition hits in. I don't like this part, so I will call it U. And I will follow this method over here. 2 ways of doing it again. Let me show you both again, and then I'll stick to the one I personally like. If U is 5x, and you say in your head, like, let U be 5x. When you say it this way, you take responsibility for your choice, and if it's wrong, you know, you just choose something else. Don't be afraid. Sometimes you have to do a couple tries, and then you get the answer. Choose something else. Then du is, what is derivative of 5x? That's 5, and then forget dx. Put it in the brackets. Okay, 2 ways of seeing the situation. I know the integral will become e to the u, because 5x will be named u. But what happens with dx? Way 1, I want dx to be 5dx, because I have it over here. So let's multiply by 5 and then make it happen. You know, that's why I kind of like it because I'm in control of it. I want it to be 5dx, so I just put 5 in it. And then I I trigger myself and I say, wait, you can't just put numbers with no consequences. Then I will divide by 5 outside of the integral. This makes sense. So I'm making it look good. I'm making it look the way I want it. Then all this piece becomes du. Integral becomes e to the u du. What is the integral of e to the u du? E to the u. All agree? E to the u. Plus c, don't forget. But did I lose anything? Yes. You see that's 1/5? Don't forget it. I will be doing it a couple of times for you to make sure you don't lose it. That's when you're going to be checking your answer and it's not going to match unless you have this 1/5 in front of the integral. You will differentiate and the chain will not match unless you have 1/5 there. That 1/5 basically cancels out the 5. We don't know, nobody knows except you what u is. So I'll remind myself that u is 5x and complete the example. The example is, the answer is 1/5 e to the u is 5x plus c. At some point you will start skipping this step. At some point you will realize that you can skip this step I just underlined. You know it's going to be 1/5 e to the u, so just plug your u right away. That speeds up exams quite a lot. If you're not a very creative person, maybe you are, you just don't think that you are. So I do recommend you to stick to this method. But if you did not get how I got this 5dx thing, why did I even get this 5dx thing? Then this is what I teach way 2. When you set u to be 5x, then you found du is 5dx. Solve for dx. So I will choose green color. Dx will be 1/5 du. And then you plug in, and I'll even number them. You plug in equation number 1 and equation number 3. So it's 1, 2, and 3. 1 is where you set up your u. 2 is when you differentiate u. 3 when you solve for dx. You plug in 1 and 3 into your integral. And then it just works out itself, like I showed you in the first example. And you don't have to be creative and you don't have to multiply by 5 and divide by 5. When you plug this dx and you plug this u, it just works it out by itself. So way 1, way 2. If you freak out during the exam, do the second way. But if you can handle the imagination thing, I think it's just faster this way. And definitely less messy. Okay, shortcuts. So my students love my first lectures of Calculus 2 class because I will give you very good shortcuts. In other classes, they don't teach it for some reason. With these shortcuts, your exam becomes so fast, you will see. And I put it in my solutions key, so you will see them a lot. Shortcut. And these shortcuts are amazing. The first shortcut is when you see an integral with the exponential function and the linear at the top over here, the linear means no squares, no square roots, it's ax plus b, that's what linear means. So what's important here is this a in front of the x, that's gonna be the important piece. In general, you just have a formula for it. And again, it's a shortcut, it's not actually a formula, we don't require you to memorize it. The formula says, since the derivative of exponential function is the same exponential function with general, and integral of exponential functions is the same, you know it's going to be still e to the same ax plus b, but based on the chain rule, when you differentiate e raised to the ax plus b, you multiply by a. When you integrate, you undo the result. So you divide by a over here, and don't forget plus c. And that's the amazing shortcuts. That's a shortcut number 1 we saw. And I'll give you the shortcut for sine, cosine, square root, e, and log, and you will see how amazing they are. Let's check what we got. We had integral of e to the 5x dx. Based on this formula, the answer will be 1/5 integral to the same 5x plus c. Exactly the same. I just gave you the answer like this as a shortcut. So that's a pretty cool thing. You will be using it. You will see it's like basically magic, but it's a shortcut for the U-substitution. It's not a formula or anything. It's literally a shortcut. It skips all the U-substitution because we will teach you to do U-substitution in your head. I will use red color as pink. I will use pink color over here to show you A is important because we're going to be dividing by A over here. So this leading coefficient is the one that pops out from the linear part. Questions? Unmute yourself and ask, or type if you are shy. Because I will do number 3. Let's do second example. What do you think? Yeah, chat. You can use chat if you have questions. Why it's not sticking to here? So not get distributed. Oh, very good question. Why we had, interesting that I don't see it here. Okay, fine. My chat is glitching. I know why. Co-host, more. Okay, now it should be good. Why over here, 1/2 or 1/5 did not distribute to plus C part, especially over here? Very good question. I had 1/2, huge parenthesis, U and plus C. Then I multiplied 1/2 by U, but I never multiplied 1/2 by C. That is because 1/2 and C are both constants. C is a general constant that collects all the constants inside. So C just swell up to the 1/2. You can call it C1 if you want, so you can rename it. But basically C represents all the constants laying around the field. C absorbs all of them together. Soon we're gonna have several, you'll see. When we're gonna do integration by parts, you will have like 2-3 constants popping out and we're all gonna collect them into C, capital C. Very good question though. Okay, good. Third example with tangent, let's do some trigonometric functions, of course. Cannot leave without those trigonometric functions, your favorite ones, I'm pretty sure. Tangent X. Did you miss tangents? Did you miss tangents in your life? Tangent X. This class will have lots of trigonometry, so just for you to know, that's the fact. Tangent X. What is the integral of tangent? Very interesting. So we're differentiating everything we know. We know how to differentiate tangent, right? The secant square thingy. Then we know how to do sine, cosine, exponential functions, square roots. But now we're trying to undo that. So interesting. What happened to some kind of function? The derivative of that function gave you tangent. Pretty cool idea. We actually don't know that. We need to figure it out. What is the integral of tangent? It should be something. So you'll be surprised, but it's actually log. That's a huge, weird idea that log pops out from the trigonometric function somehow. That's crazy that logarithmic function just shows up from nowhere. Let's see why. If you don't know how to integrate something and we're just learning integration by parts and U-substitution, integration by parts comes on Wednesday, then you see the trigonometric function, you stuck, you feel miserable, don't stuck too much. The first step I would recommend you to do is to rewrite whatever you know. I know that tangent is sine over cosine, and maybe at least writing down some information will make you feel better. And when you feel better, your brain gets endorphins and maybe it will give you more solutions out of this. So I wrote this down, looks not too bad, and now actually I can try to do U-substitution. I will show you one idea here, how the U-substitution is working. U-substitution, this first example actually is very good explaining it. U-substitution works when there is an integral in front of you and some piece of that integral is a derivative of another piece of the integral. So x to the 4 plus 2 is the function. When you differentiate this function, it gives you 4x cubed dx. So 4x cubed dx is the piece that is a derivative of some other piece. And that's exactly where U-substitution should be used. That's how you should remember it. You see that some piece looks like close to it, a derivative of another piece. Then you do U-substitution. Why I'm saying looks close? Because in this example with E, 5x derivative is 5, and here it is. So like it should be close to it. It may be not there, but at least it looks close. Do you see in front of you a function that will give you another function when you differentiate it? You see, like that's a cool idea here. I see both. Derivative of sine is cosine, and derivative of cosine is sine, but with negative sign. That is the key. If you see that, it's supposed to hit your intuition. Oh, probably I should use U-substitution. because one piece of the integral is a derivative of another piece. And now ask yourself, do you want to deal with something in the denominator or with something in the numerator? Which one you don't like more? And the one you don't like more, make it u. So that's how I teach it. And damn, it works. It's exactly how the logic works here. I don't like this guy in the denominator, so I will call that guy to be u. Make sense? And since cosine ended up to be in denominator, that's a coincidence. If I will work with arctangent, then sine will be in the denominator. Then I will make sine u. But since cosine end up to be in the denominator, I don't like it. And I like, dude, you are messing everything up. I cannot divide by you if you're 0, those kind of things. And I'll make that piece to be u. Let's see how it's gonna work. Let u to be cosine x because it's in denominator. Then du is minus sine x, that's derivative of cosine. Don't forget dx. Put it in the brackets. And now, interesting thing. So if I'm having u in the denominator, that's cosine, the du piece is minus sine x, and I do have sine x dx, right? So derivative is minus sine x dx. I have just sine x dx. That's why I really recommend you to do the way one creative way. The creative way says you need minus sine x dx, but you have just sine x dx. Then make it minus. Why not? Multiply by -1 inside and outside. Boom, done. Then it's complete match. So I put it in the blue color for you to know that this piece, I just made it by myself. It was not there originally. But minus times minus is plus. So I did not mess it up, but I made it better for myself. If now I have minus sine x at the top, then the whole top piece, which is numerator of that fraction, is now can be called du. And I have a new integral to work with. A new integral becomes minus in front, a huge integral with du over u. Du over u. What do you think? Du over u. With minus in front of it. What is the integral of du over u? You're probably a little bit confused. You don't remember it. Okay, then write it down. Minus 1 over u du. That's the same thing. You don't have to do du over u, even though actually it saves space when you write, so I like it this way. Then, what is, I reviewed it in lecture 0. What is integral of 1 over u? Natural log of absolute value. Natural log of absolute value u plus c with negative in front of it. You can put it all in blue color if you want, because that's the one we made. Well, remember by hand. What is your u? Finally, I will just jump into the result right away. Well, I will write down. U is cosine. So the answer will be minus natural log absolute value, because log doesn't exist for negatives and 0. So absolute value is important. Cosine x plus c shapes, and that's the answer. So shocking that somehow when you differentiate, so what is the speed if you have distance negative log of absolute value of cosine x plus c? To find speed out of this distance, you actually differentiating it. And surprisingly, when you differentiate natural negative log of cosine, it becomes tangent. So tangent is a speed with the given distance as negative log of absolute value of cosine x. Shocking. That's an interesting connection between trigonometric function and logarithmic function. Pretty cool. And basically it slows down. You see, tangent exists by itself. Log is the function that slows down processes. So apparently log showed up and it's slowing down the cosine, and the cosine is a vibration or escalator. It goes up and down like a sound. So pretty interesting. The tangent has a connection with log, which is slowing down function, and the cosine. In general, there's a formula which I will never force you to remember. I hate forcing students memorizing formula. My memory is bad, so I struggled a lot when I was forced to do it. That's why I always honestly tell you which formulas you need to know and which one you don't. This one you don't. Integral of tangent x in the book is written as natural log of secant x plus c. It's the same thing. How come? Because properties of natural logarithm tells you that this negative sign can be put over here at the top. Then it becomes 1 over cosine. And 1 over cosine is secant. I will do because BC. 1 over cosine x is secant x. And the property of logarithms allows you to put this negative in front of the log up here to the exponent. Cosine raised to the negative 1 becomes 1 over cosine. Pretty cool. Pretty cool.